Welcome to Temple AK Academy and welcome to the physics class today. We're going to discuss a very important topic today, the resolution of forces. This is a topic very important in the understanding of mechanics as an aspect of physics. Resolution of forces plays a major role in understanding other topics like equilibrium, where we see the principle of moments, machines, and many other areas of mechanics. So it is a very important aspect. I encourage you that your time spent watching this video is going to be rewarding. Let us get in very quickly and see resolution of forces. Yeah, let's look at the definition of resolution of forces. It involves resolving forces into their components. How to resolve the force into components. Let's go straight off with the definition. Resolution is the process of splitting a force into two perpendicular forces known as components. And these components are usually at right angles to each other. When taken together, they produce the same effect in magnitude and direction as the original force. The same effect in magnitude and direction as the original force. Let us go straight into the process. How is it done? So to resolve the force, we consider two things. Number one, the direction in which the force is acting. You can see in this diagram, the force F acts along that direction as indicated by the arrow, which means it originates from that point known as the tail of the vector. This force F acts at an angle theta degrees to the horizontal direction. And therefore, we start straight up showing the two components. The components will be by construction. Construct two lines that are perpendicular such that the given force F lies between them. The given force F must lie between them. As you can see, the force F is in between the vertical component and the horizontal component. Beautiful. Now, let us assign their magnitude. Let the horizontal component take on the value F sub x, which means F in the x direction. But let the vertical component take on the magnitude F sub y. Good. Now we do what I've decided to call a blockade. The term blockade is not expressed in many of the textbooks in physics, but I've decided to introduce it to facilitate the understanding of this topic. I call it the blockade. The blockade. The blockade is simply a line drawn to close up a right angle triangle. Not anyhow, of course. It must be such that the angle given lies within the right angle triangle form. That is the blockade. So this is the blockade. The blockade has this orientation, vertical orientation now. Therefore, we're going to carry the magnitude of this vertical component onto that side, F sub y. And this is F sub x, while you have the force F. So we have a right angle triangle with the angle within. Let us label this triangle. I will call it triangle O from the origin, A at that point, then to B at that point. That's right. And now, for a right angle triangle where we're given an angle, we can make use of trigonometric ratio as illustrated by the acronym SOHCAHTOA. SOHCAHTOA. SOHCAHTOA shows the relationship between the given angle and the size of the right angle triangle. O stands for opposite, hypotenuse, adjacent. That's right. And now in this right angle triangle, the side facing the angle 90, which is that, is the hypotenuse. The side facing the given angle theta, that is the opposite. And the remaining side not yet classified is the adjacent. So we have now the opposite, the hypotenuse, and of course the adjacent. And we can achieve our aim right now. So I started off by taking cosine for reasons that will be obvious very soon. If I take cosine of the angle, cos theta cosine of the angle cos theta is the ratio of the adjacent, as we have it here, adjacent to the hypotenuse. And now the adjacent is this force fx, as we can see, that side, f sub x. So I have f sub x divided by the hypotenuse. And the hypotenuse is f. And now if we cross multiply, we're going to have, to aid the cross multiplication process, let me have over 1 here. So f cos theta matches f sub x. So I like to write fx times 1, that's fx, will be equal to f cos theta, of course. So we have the magnitude of the first component, f cos theta. And in a similar manner, I can have the sine of the angle, sine theta. In sine, we have opposite divided by hypotenuse. The opposite, of course, f sub y. So fy divided by the hypotenuse, of course, which is f. And the same way we did it in the first case, we can cross multiply right away and generate fy times 1, that is f sub y, and it's equal to f times sine theta, and that is f sine theta. Beautiful. So we have been able to develop the component. Fx is f cos theta. Let us load it. Fx is actually f cos theta. And the second one, fy is f sine theta. Fy is now f sine theta. That's right. At this point, we can wring out the original force, having developed the component. Here's the force F is no longer there. It has been replaced by the two perpendicular forces, the components. So we can show them right there. This is equivalent to, this is equivalent now to what we have. The vertical component and the horizontal component. So here we go. Now we have the component clearly. Let's indicate their arrowheads. That's right. And they are right angles to each other. Now we lose their magnitude. Fx, the horizontal one, will give f cos theta. That's it. And the vertical, fy, which is actually f sine theta. And now mission completed. The original force F has been broken up into two component forces, f sine theta and f cos theta. Now, what are the generalizations here? The two components must take on the magnitude of the original force. You can see F present in each of them. And now, one of them will take sine of the given angle, while the other one will take cos of the given angle. The final generalization I want you to maintain here is the use of the blockade. And as a general rule, the blockade, or the force with the same orientation as the blockade, will always take sine of the angle. The blockade takes sine of the angle. This is the most important generalization when it comes to resolution of forces. Let us enhance our learning with the next description. Come with me as we deal with the second example. Here we are. Now we have the force F directed along that line. Look at that. It's acting at an angle theta to the horizontal. We start straight off by locating the tail of the force, and then we construct two components such that the force F lies between them. And this component must be at right angles to each other. Let us have the arrows showing their directions. And you can see, as we developed in our generalization in the first example, both of them will have the magnitude of the original force, and that is F to this, and F also to the horizontal component. One of them is going to take sine and the other one is going to take cos. But we must do the general rule that I've taught you in this lecture, the blockade. The blockade is not written in many books, of course, but I've introduced this term in order to facilitate comprehension. The blockade. The blockade is that line you draw, of course, so that you have a right angle triangle and the given angle lies within that right angle triangle. Now, get the orientation of the blockade. The blockade is actually vertical, as you can see, in that line, vertical, and therefore it will be equivalent to this vertical component. The blockade takes sine, and therefore, since it is vertical, it will impact sine to the vertical component, while the horizontal component in this case will take cos of the angle. Very simple. Now we have done the resolution. So right away, you can say this is equivalent to what we've developed. And straight up, we can wring the force out of the way. The force F has been broken up into F sine theta vertically and F cos theta vertically. So F sine theta combined with F cos theta will produce the same effect in magnitude and direction as the original force F. And therefore, we can draw a new diagram to show the resolution. So we have the horizontal component along that direction. Let me use a better color of marker. Yes. And now the vertical component along that direction, of course. This is it. Now, let us show the direction of the arrows, the arrowheads. Yes. And the arrowheads. Yes. As they are in the original constructions. Now, the magnitudes. The vertical component here, actually taking F sine theta. Let's load it. F sine theta. While the horizontal component takes F cos theta in this case. Beautiful. Now, avoid the trap. Avoid the trap, the generalization, wrong generalization that the vertical component takes sine at all times. No. And that the horizontal component takes cos. That's wrong. The only correct generalization you can have here is that the blockade takes sine at all times. Have that in your mind. The blockade takes sine, and the blockade has been shown. That line you draw to form a right angle triangle, and you have the angle given within it. Let us show our angle here, 90 degrees. So the first F has been broken into two forces, F sine theta and F cos theta. All right, there is another one to buttress our learning. Please, if you find this video exciting, interesting, and then educative, please take a moment to like this video, subscribe to this channel, and share this video with your friends, because I want you to know when I make new videos. So smash the notification bell button so that you know when I make a new video so that you can learn. All right, let's get into it. The last example. All right, here we are. Another force. As you can see, the force F acting from the origin along that direction at an angle theta to the vertical. Straight away, the components, now you're an expert in description of the components. You're an expert already. I can see that. Horizontal, and then the other one, vertical downward. Such that the given force lies between these two directions. And you can see, first, second, the force is in between them. Now you're correct. Give the arrowheads very quickly. Give the arrowhead. And now, from our rules, we know that since the magnitude of the given force is F, it will be carried onto each of the components. The difference will be one of them having sine and the other one taking cos. And now the blockade rules. Take a moment now. Pause the video. And let me see the blockade. Take a moment, pause this video, and let's have the blockade. Okay, yes. Now, well, if you have done this construction, that will not be correct. This is the wrong block. As you can see, even though there is a right angle triangle, but the given angle is now outside of that right angle triangle. So this is the wrong blockade. The correct blockade is the other one. Yes, that one. This is the correct block at right angle. And once you have the correct block, check the orientation of the block. You can see the block is horizontal. You can see that it is horizontal. So it will be equivalent to the horizontal component. Being horizontal, it will be equivalent to the horizontal component. Finally, the blockade takes sine of the angle. Therefore, the blockade being horizontal will give sine of the angle to the horizontal component. The blockade being horizontal facing the angle gives sine to that horizontal component, while the other one takes cos of the angle. So one rule you can use, you cannot miss it, you won't miss it, is that the blockade will always take the sine of the angle. Locate the blockade, give it sine, and you can't be wrong. And now we can already show our result components, of course. Horizontal, left way, vertical, downwards. Now let us load the arrowheads. Now they are arrowheads. Yes. Yes. And they are at right angles. The magnitude straight away. This vertical component takes f cos theta. And the other one takes f sine theta. Now, exactly what I told you in the previous examples, the vertical component this time around is taking cos of the angle, as you can see. While the horizontal component is now taking sine of the angle. So sine and cos can be anywhere, but something you can do and you will never be wrong is to use the concept of the blockade. If there's anything you've learned from this video, it should be how to use the concept of the blockade and stay safe. Let us finish it off with a final example. Here we are. In this final case, the first f acts in the direction shown. So let's increase speed. It has its origin at that point. It has its origin at that point. So we can already construct now the first component. That's right. And then the second component. Beautiful. Such that the original force is in between them. Arrowhead to show their directions. Then the blockade, of course. You can't miss. With the concept of the blockade, you cannot miss. Where will the blockade be? Pause the video so that you can locate it. Correct. If you have chosen that the blockade will be here, then you are correct. At right angle. Yes. Now, get the orientation of the blockade. The blockade is horizontal. And it will, of course, take sine. So the horizontal component takes sine. Both components will have the magnitude of the original vector. We have learned that. The horizontal component, just like the blockade, will take sine. So we give sine of the angle to this horizontal component and give cosine of the angle to this vertical component. And now we can draw a new diagram to show the components. All right. The horizontal, the vertical. And now it's time for their arrowheads. At right angles. Show the magnitude, f sine theta. And of course, f cos theta. These two forces will produce the same effect in magnitude and direction as the original force, which we can now wring out of the way. It is no longer there. It has been split into its components. Okay, you can take a moment to review this video, and then we continue with real examples with real magnitudes and real angles. Let's go on. In this example, we see the force of 100 newtons acting in the direction shown at an angle of 30 degrees to the horizontal. Straight away we begin. Let us go for the tail of the vector. And here we are. We know how to locate the tail already. That is the tail of this vector. Construct the component. First component, vertical component through that origin. That's right. Second component, horizontal component through the same origin, such that the given force lies between the two components. Give the arrowheads to indicate direction. Both components will carry the magnitude of the original force, which is 100 newtons. So let's go. 100 newtons given to this. 100 newtons given to the second one. And now, the blockade. Remember, your operating principle, use of the blockade. The blockade takes sign, but where will the blockade be? You have learned that. Right there, of course. Because this is the only way you can close a triangle that has the angle given within. That's right. And now the blockade has a vertical orientation, as you can see. Yes, the blockade is vertical. And if you take sine, therefore the vertical component, which is this force here, right here, we take the sine of the given angle, sine of 30 in degrees. While the other one, we take the cosine of 30 in degrees. Now, with the calculator, we can know the value. Sine of 30 is half, 0.5. 100 times 0.5 will give us 50 newtons. Cos 30 is 0.8660, and therefore 100 times 0.8660 will give us 86.6 in newtons. Mission completed. Now we can show that this original drawing is now equivalent to the components. So we have the vertical component, of course, and the horizontal component at right angles to each other. That's right. Let's give the arrows. The arrows. Now we can look the values. The magnitude of the horizontal component, 86.6 newtons. Let's load it. 86.6 in newtons. And the magnitude of the vertical component, 50 newtons. And then the process is completed. So let us see the final example in this lecture. Please don't forget to subscribe to this channel. Hit the notification bell button after subscription so that you can get the notification when I make a new video, and please share this video to aid learning others. Now the final example. Very quickly, we want to resolve 80 newtons acting in the direction to the vertical at angle 60 degrees. We want to resolve this. The first thing to do is to go for the tail. That's right. Do your construction of the two components. Both of them are right angles to each other. Yes, and that's it. Vertical and horizontal components at right angles to each other. And now your blockade. Blockade is right there. You can see we've increased speed because we know what to do at angle 90, such that the given angle lies within the triangle you have highlighted. Check the orientation of the blockade. The blockade is horizontal, as you can see, horizontal, and therefore it will define the horizontal component. Meanwhile, both components will start up their magnitudes with that of the original vector, 80 to each one of them. Now, one of them takes sine, while the other one takes cos. The one that takes sine is the one with the orientation of the blockade. The blockade is horizontal, therefore the horizontal component takes sine. Sine of the given angle, 60 degrees. And of course, we have cos of the given angle, 60 degrees. Now, with an electronic calculator, we can take the values. Cos of 60 degrees is 0.5. 80 times 0.5 will give you 40 newtons. 40 newtons. And the sine of 60 degrees is 0.8660 multiplied by 80, we have 69.28 newtons. 69.28 in newtons. Mission completed. And now, this is equivalent to our new arrangement of forces. The horizontal and, of course, the vertical. That's right. At right angles to each other. Arrowhead showing their direction. And now loading of their magnitude. The horizontal has the magnitude 69.28 newtons, 69.28 newtons, and the vertical 40 newtons. That's why. Mission completed. So this is the simple process of resolution for forces. Now you can review what you have learned so far in this video. Don't forget to subscribe to this channel and like and share the video. Now, finally, I have practice for you. Don't go away. I have practice for you. I have practice for you. Yes. Um, it's time for you to practice. Yes, I have practice for you because practice is very important for your development. I actually made a post, and this is the YouTube. You can find it on my YouTube channel by clicking this link. You see a video dedicated to you to understand why you have to practice. So you can consider that. All right. Now here we go. So resolve each of the following forces into two perpendicular components. And that's it. The first 50 newtons acting at an angle of 30 degrees to the horizontal. Second question, 60 newtons acting at 45 degrees to the vertical. Third question, 80 newtons acting at angle 60 degrees to the vertical. And finally, 120 newtons acting at 40 degrees to the horizontal. Here, of course, I decided to give you an angle that is not a special angle. So rely on an electronic calculator for your computation here. Once you're ready, you take a look at your answers, and you can pause at any time you want to solve these exercises. So your answers, the answer key is up next, of course. Fx shows the horizontal component. In this case, Fy shows the vertical component. So whenever you decide to practice, please check your answer. And of course, my favorite quote, mastery and expertise are products of persistence and consistency in practice. And that's the original quote credited to me. You can click on this link to watch a short narration on this quote on my channel. Please subscribe to this channel and hit the bell notification for subsequent videos. Share this video to your friends. Thank you for watching. Until I come your way next time, stay blessed, remain solid, keep your practice up. Thank you.